Picture this. You're holding a clay tablet in your hands, fresh from the kiln, still warm. The year is 1800 BCE. You're standing in ancient Babylon in what we now call Iraq, and you've just solved a quadratic equation. Yes, a quadratic equation. The same type that made you question your life choices in high school algebra. Except, here's the kicker. Pythagoras won't be born for another 1,000 years. The Greeks, who everyone credits with inventing mathematics, they're still figuring out which end of a stylus to hold. And yet here you are in Mesopotamia, doing math that would make your calculus teacher weep with pride. Before we go any further, if you're the kind of person who enjoys having everything you learned in school completely flipped upside down, hit that like button and drop a comment telling me where you're watching from, because I genuinely want to know if there's anyone in modern-day Iraq watching this, connecting with their ancestors' genius. Now get comfortable, dim those lights, maybe grab some tea or whatever helps you relax, because we're about to spend the next couple hours exploring how a civilization that existed 4,000 years ago invented mathematics as we know it. And you're probably going to fall asleep, learning something that'll make you the most interesting person at your next dinner party. Let's jump in. The first thing you need to understand is that when we talk about ancient Babylonian mathematics, we're not talking about some primitive counting system where they used rocks to figure out how many sheep they owned. No, no, no. We're talking about sophisticated, abstract mathematical thinking that rivals anything produced until the Renaissance. We're talking about people who created a number system so clever, so perfectly designed, that we still use it every single day and don't even realize it. Every time you look at a clock and see 60 minutes in an hour, that's Babylon talking to you from across 4 millennia. Every time you measure an angle in 360 degrees, you're using Babylonian mathematics. These people didn't just count, they computed, they calculated. They solved problems that wouldn't be touched again for literally thousands of years. And the wildest part, we almost missed it entirely. For centuries, archaeologists were digging up these clay tablets covered in wedge-shaped marks, what we call cuneiform writing, and they had no idea what they were looking at. They thought maybe they were receipts, grocery lists, ancient bureaucratic nonsense. And sure, some of them were exactly that. But hidden among the ancient equivalents of tax forms and shipping manifests were mathematical treatises that would revolutionize our understanding of history. Imagine being the scholar who first cracked the code on one of these tablets and realized, oh my God, this is the Pythagorean theorem, except it was written 1,200 years before Pythagoras was even born. That's the equivalent of finding a smartphone in a medieval castle. It breaks everything you thought you knew about the timeline of human achievement. So let's set the scene properly. Mesopotamia, the land between two rivers, the Tigris and Euphrates. This is the cradle of civilization, and I mean that literally, not in some poetic hand-wavy sense. This is where humans first figured out how to do civilization. Agriculture, writing, cities, laws, literature, and yes, mathematics. All of it started here, in what is now modern Iraq, in a flat, hot, dusty river valley, where summer temperatures regularly hit 120 degrees Fahrenheit. Not exactly the romantic image of scholarly pursuit, is it? But here's what's fascinating. The Babylonians didn't develop mathematics for fun, or for some abstract philosophical reason like the Greeks would later claim to do. They developed it because they absolutely needed it. Think about what it takes to run a civilization. You need to track taxes. You need to measure fields so you can figure out who owns what and who owes what. You need to calculate the amount of grain in a storehouse, the number of bricks needed for a building, the depth of an irrigation canal. You need astronomy to create calendars, so you know when to plant crops. You need to predict when the rivers will flood. All of this requires math, And not just basic arithmetic. You need sophisticated calculation, algebraic thinking, geometric principles. The Babylonians rose to the challenge in a way that's honestly breathtaking. And they did it all without calculators, without computers, without even a decent pen and paper. They used clay tablets and a reed stylus to press wedge-shaped marks into soft clay, then baked the tablets to preserve them. It's like trying to do your calculus homework by poking a stick into mud and then putting it in an oven. And yet it worked so well that thousands of these tablets survive to the present day, giving us a window into their mathematical minds. Now I know what you're thinking. Okay, smart person on YouTube, if they were so advanced, why did it take us so long to figure this out? Great question. Hypothetical viewer. The answer is partly about language, partly about assumptions, and partly about academic snobbery. For a long time, Western scholars had this narrative that mathematics, real mathematics, started with the Greeks. Euclid, Pythagoras, Archimedes, these were the heroes of the story. Everything before them was considered primitive, basic, not really worth serious attention. This Eurocentric view of history meant that when scholars encountered Babylonian mathematical tablets, they didn't take them seriously at first. It wasn't until the early 20th century that people like Otto Neugebauer started really digging into these texts and going, wait a minute, hold on, this is incredibly sophisticated. These tablets reveal a mathematical tradition that was already ancient by the time the Greeks got started. And once scholars started paying attention, the floodgates opened. Tablet after tablet revealed mathematical problems, solutions, tables, and techniques. We found multiplication tables that go up to absurd numbers. We found tables of reciprocals, which is a fancy way of saying they'd figured out division in their sexagesimal system. We found geometric problems involving areas and volumes. We found algebraic equations, sometimes stated as word problems, sometimes in a form that's recognizably algebraic, even to modern eyes. Let me give you an example that'll blow your mind. There's a tablet called Plimpton 322, currently sitting in Columbia University, and it's basically a table of Pythagorean triples. These are sets of three numbers that satisfy the equation a squared plus b squared equals c squared. The tablet lists 15 rows of these triples, and they're not simple ones. We're talking about numbers in the thousands. This tablet was created around 1800 BCE, and for decades mathematicians have argued about what exactly it represents. Is it a teaching tool? A reference table? Evidence of an understanding of the Pythagorean theorem centuries before Pythagoras? The answer is probably yes to all of the above, and that's the point. These weren't mathematical dabblers. These were people who understood number relationships at a deep, structural level. They weren't just memorizing formulas, they were exploring the nature of numbers themselves, and they did it without our modern notation, without our symbolic algebra, using a number system that seems bizarre to us, but was perfectly logical to them. Speaking of which, we need to talk about that number system, because it's both genius and slightly maddening. The Babylonians used a base 60 system, called sexagesimal. We use base 10, probably because we have 10 fingers. Makes sense, right? But the Babylonians went with 60, and before you ask, no, nobody's entirely sure why. Maybe it's because 60 has a lot of divisors. You can divide 60 evenly by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30 and 60. That's incredibly useful for practical calculations, especially fractions. So here you are, apprenticed to a scribe in ancient Babylon. It's your first day in the tablet house, what we'd call a school. Except imagine school took place in a small hot room with no air conditioning, no chairs, just you sitting cross-legged on a floor that's probably seen better days. Your teacher, the Umia, is a stern-looking individual who doesn't believe in positive reinforcement. Get something wrong and you're getting whacked with a reed, because that's just how education worked back then. Fun times. Your first lesson is learning the number system, and let me tell you, it's a trip. The Babylonians represented numbers using just two symbols, a vertical wedge for 1 and a corner wedge for 10. Seems simple enough, right? You can make any number from 1 to 59 using combinations of these. Want to write 23? That's 2 corner wedges for 20 and 3 vertical wedges for 3. Easy. But here's where it gets spicy. Once you hit 60, you don't get a new symbol. Instead, you start over with the same symbols, but now they represent a different place value. Just like in our system, where the same digit 5 can mean 550 or 500 depending on where it sits. In the Babylonian system, the same combination of wedges could mean different things depending on position. Except, and this is crucial, they didn't always use a placeholder for 0, not until much later, anyway. So you'd have to figure out from context whether a symbol meant 1 or 60 or 3600. It's like trying to read a number where someone randomly removed the commas and decimal points. You just have to vibe with it and hope you're right. If this sounds confusing, that's because it absolutely is when you first encounter it. But the Babylonians lived and breathed this system, and for them it was as natural as our base 10 is for us. And honestly, for certain types of calculations, their system was superior. Try dividing something by 3 in base 10. You get 0.333 repeating forever, which is annoying. In base 60, 1/3 is just 20. Clean, simple, done. The sexagesimal system made certain fractions beautifully elegant. This is why the system survived for astronomy and timekeeping. When you're tracking the movements of stars and planets across the sky, you need precision, and you need fractions that don't turn into endless decimals. The Babylonians figured this out 4,000 years ago, and the system was so good we never bothered replacing it. Your smartphone, your watch, the GPS in your car, all of them are using Babylonian mathematics every single time they measure time or angles. Let that sink in for a moment. Now back to you in the tablet house. You've learned the basic numbers, and now your teacher is making you write them over and over. You take a lump of soft clay, flatten it into a tablet shape, and use your reed stylus to press in the wedges. It's harder than it looks. Press too hard and you gouge the clay. Too soft and the mark disappears. You need just the right angle, just the right pressure. Your hand cramps. Your back hurts from sitting on the floor. The kid next to you keeps getting hit with the reed because he can't remember how to write 47. You're starting to wonder if maybe farming would have been a better career choice. But you persist, because being a scribe is one of the few paths to a comfortable life in Babylon. If you can master mathematics, you can work for the temple, or the palace, or wealthy merchants. You'll never go hungry. You'll have status, so you keep pressing those wedges into clay, over and over, until your fingers move automatically, and the numbers start to make sense. After weeks of this, you graduate to multiplication tables, and oh boy, the Babylonians loved their tables. They created extensive reference tablets, covering every multiplication, division, and reciprocal you might need. These weren't just simple times tables like you memorized in 3rd grade. We're talking comprehensive mathematical reference works. Need to multiply 44 by 26. There's a tablet for that. Need the reciprocal of 81. Tablet. Need to calculate the area of an irregular field? The Babylonians essentially created the ancient world's version of a calculator, except it was made of baked clay and could survive being buried in the desert for 4,000 years. Try that with your iPhone. One of the most famous sets of tablets is the YBC collection at Yale University. These tablets show student exercises, teacher demonstrations, and reference tables. You can see the progression from basic problems to increasingly complex ones. It's like looking at someone's math homework from 2000 BCE, complete with mistakes, corrections, and presumably frustrated erasing, except you can't really erase clay, so they'd just start over. The tablet YBC 7289 is particularly mind-blowing. It shows a square with its diagonals drawn, and written on it is the approximation for the square root of 2, accurate to 6 decimal places. That's 1.414213, comma for those keeping track at home. They calculated this without calculators, without decimal notation as we know it, using their sexagesimal system and pure mathematical reasoning. The accuracy is stunning. Modern calculators give you 1.41421356, comma, so they were off by only 0.0000000056. That's the kind of precision that makes modern mathematicians weep with joy, and perhaps a little professional jealousy. How did they do it? We think they used an iterative method, essentially making better and better guesses, but we can't be entirely sure because they didn't always show their work. Babylonian mathematical tablets usually show the problem and the answer, but not always the method. It's like they assumed anyone reading it would already know the procedure, which is both frustrating for modern scholars and a testament to how common this mathematical knowledge was among educated Babylonians. Imagine if your math teacher just wrote the answer on the board and said, "Obviously you all know how I got this," you'd riot. But in Babylon this was normal. Let's talk about what you'd actually do with all this mathematical knowledge once you finished your training. Say you're now a working scribe, and a merchant comes to you with a problem. He's got a rectangular field, and he knows the area is 600 square units, and the length is 10 units more than the width. What are the dimensions? This is a classic quadratic equation problem. In modern notation we'd write it as x times the quantity x plus 10 equals 600. You'd solve it using the quadratic formula, which you may or may not remember from high school, depending on how much you've repressed. But the Babylonians didn't have the quadratic formula as we know it. Instead they had a procedure, a step-by-step algorithm that works every time. And here's the fascinating part. Their method is essentially the same as our quadratic formula, just expressed differently. They'd tell you to take half of the difference between length and width, square it, add the area, take the square root, then add and subtract that half difference. It's algebraic thinking, without algebraic notation. They were doing algebra before the word algebra existed. The word algebra, by the way, comes from Arabic from the title of a book written by the mathematician Al-Khwarizmi in the 9th century CE. His work was heavily influenced by earlier sources, including Babylonian mathematics that had been preserved and transmitted through various cultures. So the Babylonians invented the methods, they just didn't get naming rights. Story of their civilization, really. If you're enjoying this deep dive into ancient mathematics, do me a favor and hit that subscribe button. Also comment below and tell me what's the most complicated math you've ever had to do in real life. I'm genuinely curious whether anyone actually uses calculus outside of specific careers, or if we all just calculate tips and grocery budgets. Now let's get back to your life as a Babylonian mathematician. Another common problem you'd encounter involves compound interest, because yes, banking and loans existed in ancient Babylon, and yes, they charged interest, and yes, people needed to calculate how much they'd owe. The sun is directly overhead now, turning the clay tablet house into an oven within an oven. You're practicing geometry problems, which means you're about to discover that the Babylonians understood shapes and spaces in ways that would make Euclid look like he was just getting started. And technically, he was just getting started, because he wouldn't write his famous elements for another 1500 years. You're given a problem about a circle. A farmer needs to know how much rope to use to create a circular irrigation boundary. You need to figure out the circumference given the diameter. Now this requires knowing the relationship between a circle's diameter and its circumference, what we call pi. The Babylonians knew about pi. They didn't call it pi. That's a Greek letter that wouldn't be used for this purpose until much later, but they knew the ratio. Their approximation was 3, or sometimes 3 and 1/8, which equals 3.125. Not as accurate as the modern value of 3.14159 and so on, but close enough for practical purposes like figuring out irrigation boundaries or building circular structures. The fact that they recognized this as a constant relationship, that every circle follows the same rule regardless of size, shows sophisticated geometric thinking. They understood that mathematics describes universal truths, patterns that exist independent of any particular measurement. That's a profound philosophical realization wrapped up in a practical farming problem. Let's talk about another tablet, one that absolutely rocks the foundations of mathematical history. It's called BM 13901, held in the British Museum, and it contains geometric problems that are solved using what we'd recognize as algebraic methods. One problem describes a rectangle where you know the area and the difference between the length and width, and you need to find the actual dimensions. The solution method is pure algebra. The scribe takes you through a process of manipulation, of adding and subtracting, of squaring and taking roots, all described in words rather than symbols, but unmistakably algebraic. This is abstract mathematical thinking. This isn't just I have 7 sheep and I get 3 more. How many sheep do I have? This is I have an unknown quantity, I can manipulate it according to consistent rules, and I can solve for it. That's algebra. That's the foundation of all higher mathematics. And it's being done on a clay tablet in Mesopotamia, while most of Europe is still figuring out bronze metallurgy. The Babylonians also understood what we call the Pythagorean theorem, the idea that in a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. We've already mentioned Plimpton 322, but there are other tablets that show this knowledge in action. They'd use it for surveying land, for construction, for any situation where you need to calculate distances or ensure right angles. Ancient builders needed mathematics just as much as modern engineers do. Probably more, actually, because they couldn't just pull out a calculator or use computer-aided design software. Every calculation was done by hand, on clay, and if you messed up the math, your building fell down and probably killed people. So there was a strong incentive to get it right. The margin for error was, shall we say, highly motivating. You're also learning about volumes, because storing grain is a big deal in an agricultural civilization. You need to know how much grain fits in a cylindrical silo, or a rectangular storehouse, or a conical pile. The Babylonians had formulas for all of these. Some were exact, some were approximations, but they were all practical and usable. For a cylinder, they knew to multiply the base area by the height. For a cone or pyramid, they knew you needed to adjust for the tapering, though their formula for a cone's volume wasn't always accurate. They approximated it in ways that were close enough for government work, as we might say. The fact that they were attempting these calculations at all shows how far their mathematical thinking had advanced. These aren't obvious relationships. You can't just look at a cone and intuitively know its volume. You have to think abstractly to understand the relationship between dimensions and space. Now let's talk about something that doesn't get enough credit in the story of Babylonian mathematics. The tables. Oh, the tables. If you thought multiplication tables were boring in elementary school, you haven't seen anything yet. The Babylonians created tables for everything. Reciprocal tables, multiplication tables, square tables, cube tables, square root tables, cube root tables. They had tables of constants used in specific types of calculations. They had coefficient tables for solving standard problems. These tablets weren't just reference materials, they were teaching tools, calculation aids, and demonstrations of mathematical relationships. Finding patterns in numbers was apparently a popular intellectual pursuit, sort of like Sudoku but carved into clay and baked for posterity. One particularly interesting set of tables deals with exponents and powers. The Babylonians understood exponential growth, which you need if you're calculating compound interest or population growth, or how quickly grain multiplies after planting. They could calculate powers of numbers and work backwards to find roots. This is sophisticated number theory, the kind of thing that wouldn't be formalized in Europe until the Renaissance at the earliest. Let me paint you a picture of what mathematical education looked like in practice. You're in the tablet house, surrounded by dozens of other students, all boys, because this is ancient Babylon and gender equality wasn't really on the agenda. The noise is constant, the scratch of styluses on clay, the occasional thwack of the teacher's reed finding its target, whispered consultations between students, the sound of someone outside trying to sell bread. You're working through a problem set, copying from a master tablet. The problems progress in difficulty. First simple multiplication, then division using reciprocals, then areas of fields with irregular shapes, which requires breaking them down into triangles and rectangles, calculating each piece, and summing them up. Then problems involving unknown quantities, where you have to work backwards from known results to find the original numbers. These are algebraic problems, even if they're phrased as stories about grain and silver and field measurements. The abstraction is there, the mathematical thinking is there, the methodology is rigorous and consistent, and you're learning all this as a teenager in ancient Mesopotamia, while your European counterparts won't tackle these concepts for literally thousands of years. Take a moment and really think about that, really let it sink in. When Plato was founding his academy in Athens, considered one of the great moments in Western intellectual history, he was working with mathematical knowledge that was already ancient. The geometric principles he discussed, the mathematical philosophy he explored, it was all building on foundations laid by cultures to the east, foundations that were already over 1,000 years old. The story we often get taught in school has mathematics springing fully formed from the head of Greek civilization, like Athena from Zeus. But that's not what happened. The Greeks inherited, adapted, and built upon mathematical traditions from Egypt and Mesopotamia. They made huge contributions, absolutely, and we shouldn't diminish that. But they didn't start from zero. They stood on the shoulders of Babylonian giants. Now you might wonder, if the Babylonians were so advanced, why didn't their mathematics continue to develop? Why did it seem to plateau and eventually fade rather than evolving continuously like it did in later civilizations? The answer is complex, involving the rise and fall of empires, shifts in political power, changes in trade routes, and the general chaos of history. Mesopotamia saw wave after wave of conquest. Assyrians, Persians, Greeks under Alexander, Parthians, Romans, Sassanids. Each conquest disrupted the transmission of knowledge. Libraries burned, scribal traditions were lost, the cuneiform script itself fell out of use, replaced by Aramaic alphabetic writing. Once cuneiform was no longer taught, the mathematical tablets became unreadable, their knowledge locked away until modern archaeology and linguistics could recover it. Let's shift our perspective now and look at the night sky. Because Babylonian mathematics wasn't just about earthly concerns like taxes and field measurements. Some of their most sophisticated mathematical work was in astronomy, tracking the movements of celestial bodies with an accuracy that's frankly stunning given their tools. You're standing on the roof of a building in Babylon, one of the designated observation platforms where scribes track the heavens. It's night. The air has finally cooled from the scorching daytime heat, and above you the sky is absolutely packed with stars. No light pollution, no haze, just the naked cosmos in all its glory. You can see the Milky Way as a river of light across the sky. You can pick out the planets with ease, bright wandering stars that move against the fixed background of constellations. Your job tonight is to record the position of Venus. The Babylonians were obsessed with Venus. They tracked it meticulously, recording its appearances and disappearances, its positions relative to stars, its cycles. They knew Venus was both the morning star and evening star, the same celestial object appearing in different parts of the sky at different times of year. They could predict its movements with remarkable accuracy. Why? Partly for calendrical purposes, to track the seasons and know when to plant and harvest. Partly for religious reasons, because celestial bodies were associated with gods and their movements were thought to have significance for earthly events. And partly, I suspect, because some Babylonian astronomers just found it intellectually satisfying to figure out the patterns. There's something deeply human about looking at apparent chaos and finding the hidden order within it. The Babylonians created astronomical diaries, continuous records of celestial observations spanning centuries. These weren't just casual notes. They were systematic, rigorous observations including positions of planets, times of eclipses, weather conditions, river levels, market prices. Everything that might be relevant was recorded, creating an enormous database of information. And once you have data, you can find patterns. Once you have patterns, you can make predictions. The Babylonians developed methods to predict lunar eclipses with impressive accuracy. They knew the Cyrus cycle, a period of about 18 years after which eclipses repeat in similar patterns. They could tell you months or even years in advance when an eclipse would occur. Think about what that takes mathematically. You need to track the moon's position and motion. You need to understand the sun's apparent motion through the sky. You need to calculate when and where their paths will align in a way that causes an eclipse. You need to account for the fact that these cycles aren't perfectly regular, that there are variations and perturbations. The mathematics involved is complex, involving what we'd now call periodic functions and prediction algorithms. The Babylonians didn't have trigonometry as we know it, but they had arithmetical schemes that accomplished the same goals. They used what modern historians call zigzag functions and step functions, mathematical techniques that could model the changing speed of the moon's motion across the sky. The moon doesn't move at a constant speed, it speeds up and slows down in a predictable pattern. The Babylonians figured this out through careful observation and created mathematical models to describe it. Let me be clear about how impressive this is. They were modeling periodic motion, essentially doing early versions of what would eventually become trigonometry and calculus, using nothing but arithmetic and geometric reasoning in a base 60-number system, recording everything on clay tablets. If you're not amazed by this, you're not paying attention. Drop a comment and tell me what modern technology you think you could recreate if you were somehow transported back to ancient Babylon. Could you build a radio, a steam engine, or would you just introduce improved plumbing and call it a win? I think about this more than is probably healthy. Back on your observation platform, you're making careful notes of Venus's position relative to certain reference stars. You measure angles by holding up calibrated tools, basically ancient versions of a protractor. You note the time using a water clock. Because accurate timekeeping is essential for astronomy, you record everything in the standard format on a clay tablet, using the precise terminology that's been developed over centuries of astronomical observation. This tablet will be added to the archives, where it joins thousands of others, decades or centuries from now. Another astronomer will pull these tablets and use them to refine predictions, to identify even longer cycles, to deepen humanity's understanding of the cosmos. You're contributing to a multi-generational scientific project, even though the word science won't exist for thousands of years. The Babylonians identified the zodiac, the band of constellations through which the sun, moon, and planets appear to move. They divided it into 12 sections, the 12 signs we still reference today, though our modern astrology is quite different from their astronomical observations. Each sign covered 30 degrees of the sky's circle, and here we see that base 60 system again. 12 signs times 30 degrees equals 360 degrees in a full circle. This division, completely arbitrary from a mathematical standpoint, has persisted for 4,000 years because it works so well. They tracked the cycles of the planets, Jupiter's 12-year cycle, Saturn's 30-year cycle, Mars's 2-year cycle. They knew these weren't perfectly regular, that the planets sometimes appeared to move backwards, what we call retrograde motion, before resuming their normal course. They developed mathematical schemes to predict these irregularities. Again, this is sophisticated mathematical modeling applied to observational data. One of the most remarkable astronomical tablets is AO 6484, which contains a procedure for calculating Jupiter's position over a period of time. The method involves calculating the area under a trapezoid to determine displacement, which is conceptually similar to integration in calculus. When this was first recognized in 2016, it made headlines because it pushed back the use of this type of mathematical technique by about 1400 years. The Babylonians were doing things with mathematics that scholars assumed weren't invented until medieval Islamic scholars and then European mathematicians of the Renaissance developed calculus. Nope, Babylon got there first. They just wrote it in cuneiform on clay, instead of publishing it in Latin, in a leather-bound book. Now you might be wondering, how much of this Babylonian astronomical and mathematical knowledge survived and influenced later civilizations? The answer is a lot. When Alexander the Great conquered Babylon in 331 BCE, Greek scholars gained access to centuries of Babylonian astronomical records and mathematical techniques. They were amazed by the sophistication of what they found. Greek astronomers like Hipparchus and Ptolemy used Babylonian data and methods in their own work. Ptolemy's Almagest, the astronomical work that dominated Western and Islamic astronomy for over 1,000 years, relies heavily on Babylonian observations. The mathematical astronomy of ancient Greece didn't emerge from nothing, it was built on Babylonian foundations. Islamic scholars during the medieval period also preserved and built upon Babylonian knowledge. The great astronomical observatories in Baghdad, Damascus, and Samarkand were continuing traditions that stretched back to ancient Mesopotamia. The mathematical techniques they used, the careful observation and recording, the predictive models, all of this had roots in Babylon, and from the Islamic world, this knowledge flowed into Europe during the Renaissance, helping to spark the scientific revolution. When Copernicus proposed his heliocentric model, when Kepler calculated his laws of planetary motion, when Newton developed calculus to describe the physics of orbital mechanics, they were all building on a foundation that included Babylonian contributions. The through line of mathematical and astronomical knowledge from ancient Mesopotamia to modern science is clear, once you start looking for it. We stand on the shoulders of giants, and some of those giants were pressing wedge shapes into wet clay 4,000 years ago. It's time we talk about the elephant in the room. Or perhaps more accurately, the clay tablet in the museum. How do we actually know all this stuff about Babylonian mathematics? How did these tablets survive? How were they discovered? And how on earth did anyone figure out what they said? Let's start with the survival part, because it's honestly miraculous. Clay tablets are both fragile and incredibly durable, which seems contradictory but makes sense when you think about it. Unbaked clay dissolves in water and crumbles easily, but fire it in a kiln, or accidentally fire it when your city burns to the ground during one of the many conquests that swept through Mesopotamia, and it becomes nearly indestructible. Ancient Babylonian tablets have survived floods, wars, building collapses, thousands of years of burial under desert sand, and accumulating archaeological layers. Paper rots, parchment degrades. Even carved stone can erode, but fired clay tablets just sit there, waiting patiently to be discovered. The downside is that they're also easily overlooked. To an untrained eye, they look like random chunks of clay. Early archaeologists sometimes discarded them or used them as landfill. It wasn't until scholars realized what they were looking at that systematic collection began. Even then, tablets were often removed from their archaeological context without proper recording, which makes it harder to date them or understand their original purpose. The history of archaeology in Mesopotamia is frankly a bit of a mess. In the 19th century, European and American archaeologists were basically treasure hunting, looking for impressive artifacts to fill museums back home. They'd dig up tells, the massive mounds that mark ancient cities, haul away everything interesting, and pay little attention to things like stratigraphy or context. Thousands of tablets were excavated and shipped to museums in London, Paris, Berlin, Philadelphia, Yale, Chicago, without careful records of exactly where they were found or what they were found with. This makes the job of modern scholars harder, because context matters. Knowing whether a tablet came from a temple, a palace, a private house, or a school changes how we interpret it. Knowing what other tablets it was found with can reveal whether it was part of a library or archive. But for many tablets, that information is lost forever. Still, we're lucky to have the tablets at all. Deciphering them was its own adventure. Cuneiform writing was a complete mystery. When European scholars first encountered it, the script was used for multiple languages: Sumerian, Akkadian, Babylonian, Assyrian, each with its own grammar and vocabulary. The same symbols could represent different sounds or concepts depending on the language and context. It's like if you had to figure out Chinese characters and Japanese kanji and Korean hanja all at once, knowing only that they looked similar and might be related. The breakthrough came in the 19th century with the decipherment of the Behistun inscription, a massive text carved into a cliff face in Iran by the Persian king Darius. It was written in 3 languages: Old Persian, Elamite, and Babylonian, all using cuneiform script. It was basically the Rosetta Stone for cuneiform. Scholars could work out the Old Persian fairly easily because they knew related languages, then use it to crack the Babylonian version. From there the floodgates opened. Suddenly thousands of tablets became readable, revealing the literature, laws, letters, and yes, mathematics of ancient Mesopotamia. But readable is a relative term. Even today, with over a century of scholarship behind us, translating cuneiform mathematical texts is challenging. The Babylonians didn't always explain their reasoning. They used technical terminology that doesn't always have clear modern equivalents. Their number system requires interpretation. A single tablet can take months or years to fully translate and understand, requiring expertise in linguistics, mathematics, history, and ancient culture. If this sounds fascinating to you, let me know in the comments if you'd ever consider becoming an archaeologist or ancient historian. It seems like the kind of career where you spend years learning dead languages and then get really excited about clay fragments, which honestly sounds amazing to me. One of the great pioneers of understanding Babylonian mathematics was Otto Neugebauer, an Austrian-American mathematician and historian of science who worked in the early to mid-20th century. He approached the tablets not just as historical curiosities, but as mathematical texts that could be analyzed using modern mathematical tools. He reconstructed their methods, identified their techniques, and revealed the sophistication of Babylonian mathematical thought. His work transformed how we understood the history of mathematics, showing that it didn't begin with the Greeks, but had much deeper and older roots. Other scholars followed, each adding pieces to the puzzle. François Thureau-Daguin worked extensively on mathematical texts. Eleanor Robson has done brilliant work on the context and pedagogy of Babylonian mathematics, showing how it was taught and used. Joran Freeberg has contributed detailed mathematical analyses of numerous tablets. The work continues today, with new tablets still being published and analyzed, new insights emerging from fresh examinations of known texts. The corpus of Babylonian mathematical tablets numbers in the hundreds that we know of, but there are likely thousands more sitting in museum basements, still uncatalogued, still unstudied, waiting for someone to recognize their significance. Every few years, a new tablet gets published that changes our understanding of some aspect of Babylonian mathematics. It's a living field of research, not some dusty historical backwater. Let's talk about some specific tablets that have shaped our understanding. We've mentioned Plimpton 322 with its Pythagorean triples. There's YBC 7289 with its accurate square root of 2. There's the tablet Viat 8389, which contains a problem about the diagonal of a rectangle and uses the Pythagorean theorem explicitly. There's IM 67118, which has algebraic problems about finding unknown quantities. Each of these tablets is a window into how the Babylonians thought about mathematical problems. Tablet BM 15285 contains a problem that translates roughly to I have subtracted the side of my square from the area, and the result is 870. What is the side? This is a quadratic equation. In modern notation, it's x squared minus x equals 870. The tablet gives the solution procedure. Take half of 1, which is 0.5, comma square it to get 0.25, comma, add 870 to get 870.25, comma, take the square root to get 2, 9.5, comma, add the original 0.5 to get 30. The side is 30, check it, 30 squared is 900, minus 30 is 870. Perfect. This is exactly the method you'd use with the quadratic formula, just expressed as a procedure rather than a formula. It's algorithmic thinking, step-by-step instructions that work every time. The Babylonians loved algorithms. They had procedures for all sorts of calculations, and scribes would memorize these procedures and apply them to new problems. What's particularly interesting is that they seem to understand that these methods were general, that they worked for any numbers, not just specific cases. That's mathematical abstraction. That's understanding the underlying structure rather than just memorizing particular solutions. Another fascinating tablet is AO 8862, which deals with a problem about exponential growth. It asks how long it will take for an amount of grain to double under certain conditions. The solution involves understanding doubling times and exponential sequences. This is compound growth calculation, the same type of math that underlies modern finance, population studies, and many other fields. The Babylonians were thinking about these concepts 4,000 years ago, not because they had a stock market, though they did have sophisticated banking and investment systems, but because mathematical patterns interested them and were useful for practical problems. Now here's a thought that should mess with your head a little. These tablets, these mathematical texts, were created by individual human beings, scribes with names, though we often don't know them. People who had lives, families, hopes, frustrations. Someone sat down and carefully pressed those cuneiform marks into soft clay, thinking through the mathematical problems, making sure the solutions were correct, creating teaching materials or reference works or records of calculations. Then they baked the tablet and put it away, probably never imagining that 4,000 years later, someone would be making a video about their work, showing it to thousands of people around the world through a technology that would seem like magic to them. The persistence of their work across such a vast gulf of time is humbling. We need to address something important now, something that complicates the simple narrative of Babylonian mathematical genius. And that's the question of sources, transmission, and the messy reality of how knowledge develops over time. The mathematics we've been discussing wasn't created in a vacuum. The Babylonians inherited and built upon earlier Sumerian mathematical traditions. The Sumerians, who developed the first cities in southern Mesopotamia around 4000 BCE, were the ones who first created cuneiform writing and began recording mathematical information. Early Sumerian tablets show counting, measurement, and administrative mathematics. The sexagesimal system itself may have Sumerian origins, though the evidence isn't entirely clear. When Semitic-speaking peoples, the Akkadians and later Babylonians, became dominant in Mesopotamia, they adopted and adapted Sumerian cultural achievements, including mathematics. So when we talk about Babylonian mathematics, we're really talking about a long tradition spanning multiple cultures and languages across thousands of years. It's not one civilization's achievement, it's a cumulative tradition. This is worth remembering, because the history of mathematics is often told as a series of individual genius moments or distinct cultural achievements, when in reality it's always been about knowledge transmission, adaptation, and incremental progress across generations and cultures. The Babylonians learned from the Sumerians, the Greeks learned from the Babylonians and Egyptians, the Romans learned from the Greeks, the Islamic scholars preserved and advanced all of the above, and European Renaissance mathematicians learned from Islamic sources. It's a chain of transmission stretching across thousands of years and multiple civilizations. Nobody invented mathematics from scratch. Everybody built on what came before. Even the great innovators, the ones who made revolutionary breakthroughs, were standing on foundations laid by others. This brings us to an uncomfortable question. Why do we, in the popular imagination, and often in education, focus so heavily on Greek mathematics, while largely ignoring or minimizing the Babylonian contributions? The answer involves Eurocentrism, the accidents of historical source preservation, and the way academic disciplines developed. For a long time, Western education was heavily focused on the Greco-Roman classical tradition. That was considered the foundation of Western civilization, the source of philosophy, democracy, literature, art, and science. Mathematics was part of that package, with Euclid's Elements held up as the perfect example of logical reasoning and geometric thought. The idea that there were equally sophisticated mathematical traditions in other parts of the world didn't fit the narrative. When evidence of advanced Babylonian mathematics emerged, it was sometimes dismissed or minimized. Scholars argued about whether it was really algebra or just arithmetic, whether it showed genuine understanding or just rote procedure. These debates often revealed more about the biases of the scholars than about the Babylonian tablets themselves. Modern scholarship has largely moved past these arguments, recognizing that Babylonian mathematics was sophisticated, abstract, and algebraic, even if it used different notation and methods than later traditions. But in popular culture and general education, the old Eurocentric narrative persists. Most people, if they think about the history of mathematics at all, picture ancient Greeks doing geometry, and maybe know something about Arabic numerals without realizing that both of those traditions were built on much older Mesopotamian foundations. This matters because it affects how we think about human achievement and cultural contributions. If we only celebrate certain civilizations while ignoring others, we get a distorted picture of history. We lose important parts of our shared human heritage. The story of mathematics is richer, more complex, and more global than the simplified version we often get taught. So let me be clear, the Babylonians invented algebra, they developed advanced geometric principles, they created mathematical astronomy that wouldn't be matched for centuries, they established mathematical traditions that directly influenced later civilizations and ultimately contributed to the mathematics we use today. They deserve recognition, not as a footnote to Greek mathematics, but as a major chapter in the story of human intellectual achievement. Let's get personal for a moment. Why does any of this matter? Why should you care about mathematical tablets created 4,000 years ago in a civilization that no longer exists? I think there are several answers. First, it's about respecting our intellectual heritage. The mathematics you learned in school, the algorithms your computer uses, the astronomy that guides satellites, all of it has roots stretching back to ancient Mesopotamia. Understanding that history gives you perspective on where knowledge comes from and how it develops. Second, it's a reminder that human intelligence and creativity aren't modern inventions. The people who lived 4,000 years ago had the same cognitive abilities we do. They were just as smart, just as curious, just as capable of abstract thought. They lacked our accumulated knowledge and technology, but they didn't lack intelligence or imagination. When you realize that ancient Babylonians were solving quadratic equations and predicting eclipses while living in mud brick cities without electricity or computers, it should inspire a sense of awe at human capability. Third, it challenges assumptions about progress and civilization. We often think of history as a steady march of progress, with each era more advanced than the last. But that's not what happened. Knowledge was gained, lost, rediscovered, transmitted across cultures, sometimes advancing and sometimes regressing. The Babylonian mathematical tradition eventually faded when cuneiform fell out of use and the cultural continuity was broken. For over 1,000 years, their achievements were literally unreadable, trapped in clay tablets nobody could interpret. Knowledge can be fragile. It requires active transmission, teaching, learning, recording. If that chain breaks, even sophisticated understanding can be lost. In our own era, we should think about what knowledge we're preserving and how, if our civilization collapsed and our digital records became unreadable, what would survive? Would future archaeologists be able to reconstruct our mathematics and science from what remained? Or would they find mysterious silicon chips and have no idea what they meant? Fourth, studying ancient mathematics is just intrinsically fascinating. If you're the kind of person who finds this sort of thing fascinating, which if you've watched this far, you probably are, there's something deeply satisfying about understanding how problems were solved with different tools and different conceptual frameworks. The Babylonians couldn't write x squared plus 5x equals 50 like we do, but they could solve that equation using their procedural methods. Seeing how they thought through problems, how they structured their solutions, gives you a different perspective on mathematics itself. It's not one monolithic thing, it's a way of thinking that can be expressed in many forms. If you're finding this interesting, hit that like button and let the algorithm know that people care about ancient mathematics. Also subscribe, because I make videos about the history of computer science, mathematics and technology, and apparently also videos designed to help you fall asleep while learning things. Comment below and tell me what other ancient civilizations you'd like to hear about. Should we do ancient Egyptian mathematics next? Indian mathematics? Chinese mathematics? Let me know. Now let's bring this back to something concrete. What would a modern mathematician think if they sat down with a collection of Babylonian mathematical tablets? The answer is they'd recognize familiar concepts expressed in unfamiliar ways. They'd see the same mathematical relationships they know. the same problem-solving strategies, the same logical structure, just written in cuneiform on clay, using a sexagesimal number system. The mathematics is universal, only the notation changes. In fact, several modern mathematicians have done exactly this, working with historians and archaeologists to analyze tablets. Their insights have helped clarify ambiguous translations and revealed mathematical techniques that historians alone might have missed. It's a beautiful example of interdisciplinary collaboration, combining expertise in ancient languages, archaeology, history and mathematics to understand texts created thousands of years ago. Some of the most exciting recent discoveries have come from applying modern mathematical analysis to ancient tablets. That 2016 paper about the Jupiter tablet, using trapezoid areas to calculate position, was a collaboration between a historian of science and a mathematician. They recognized that what the Babylonians were doing was geometrically equivalent to integration, a calculus concept. This doesn't mean the Babylonians had calculus in the modern sense, but it means they had geometric methods that accomplished similar goals for specific problems. So here we are, at the end of our journey through Babylonian mathematics. You've survived the sexagesimal number system. You've worked through algebraic problems on clay tablets. You've tracked Venus across the night sky. You've learned about the long chain of knowledge transmission that connects ancient Mesopotamia to modern mathematics. The question is, what do you take away from all this? For me, the story of Babylonian mathematics is ultimately a story about human potential. These were people living 4,000 years ago, in conditions we would find incredibly harsh, without any of the tools we consider essential for modern life, and they created mathematics that was genuinely sophisticated and advanced. They did it because they needed to for practical purposes like administration and agriculture and astronomy, but also, I think, because they wanted to, because mathematical patterns are inherently interesting and figuring them out is satisfying. That drive to understand, to find patterns, to solve problems, it's fundamental to human nature. It's not dependent on having universities or computers or published journals. It's something deeper. Give humans a problem and enough time and they'll figure out solutions. Give them data and they'll find patterns. Give them challenges and they'll develop techniques to address them. The Babylonians needed to track time and seasons, so they developed mathematical astronomy. They needed to measure fields and calculate areas, so they developed geometry. They needed to solve problems with unknown quantities, so they developed algebra. None of this was inevitable. Other ancient civilizations developed different mathematical traditions, emphasizing different aspects, using different notations, but the Babylonian approach was particularly powerful, particularly well suited to the problems they faced, and it ended up influencing the entire subsequent history of mathematics in the Western and Islamic world. That's a legacy worth acknowledging and celebrating. Now, I promised you this would be relaxing enough to fall asleep to, and if you're still awake at this point, I'm either doing a great job of being interesting or a terrible job of being boring. Either way, I'm going to shift into a more reflective, slower mode here. Let yourself relax. If you're ready to drift off, that's fine. The story is essentially complete. What follows is just some final thoughts and reflections. Think about the scribes who created these tablets. Think about a student in the tablet house, struggling to press cuneiform marks into clay, practicing number sequences until they became automatic. Think about an astronomer on a rooftop, patiently watching the sky night after night, recording positions, slowly building up a database that would be used for generations. Think about a surveyor measuring a field, calculating its area using geometric principles, making sure the tax assessment is fair. Think about a merchant calculating compound interest on a loan, using tables and algorithms to figure out what will be owed. These were real people doing real work, and the mathematical tools they created were part of their daily lives. Mathematics wasn't an abstract academic pursuit, it was practical, useful, necessary. And yet within that practical framework, they found beauty and pattern. They explored relationships between numbers, not just because they needed to for a specific calculation, but because the relationships themselves were interesting. The person who created Plimpton 322, with its table of Pythagorean triples, wasn't doing it for a specific surveying job. They were exploring number theory, finding patterns, documenting relationships. That's mathematical thinking for its own sake, driven by curiosity and intellectual satisfaction. It's the same impulse that drives mathematicians today, the same sense of wonder at the patterns that emerge from numbers and shapes. Across 4,000 years, across vast differences in culture and technology and worldview, that essential human curiosity remains the same. If you find that comforting, you're not alone. There's something deeply reassuring about connecting with the past in this way, about seeing the continuity of human thought and effort across millennia. The Babylonians are gone. Their cities are ruins. Their language is dead. But their mathematics survives, still useful, still beautiful, still teaching us about the power of human reasoning. Let me leave you with one final thought. Something to ponder as you drift off to sleep or as you go about your day. Every time you look at a clock and see it divided into 60 minutes and 60 seconds, you're using Babylonian mathematics. Every time you measure an angle in degrees out of 360, you're using their system. Every time you use algebra to solve for an unknown, you're using methods they pioneered. The ancient Babylonians are with us. In a very real sense, every single day, their intellectual legacy is woven into the fabric of modern life, so deeply that we don't even notice it. That's true immortality, not through statues or monuments, but through ideas that proved so useful and so powerful that they've survived for 4,000 years and will likely survive for thousands more. Your great-great-great-grandchildren, living in a world you can't imagine, with technology that doesn't exist yet, will still divide their hours into 60 minutes, because the Babylonians established that system and it works. Think about that. Think about the long arc of human knowledge, the chain of transmission from clay tablets to papyrus scrolls, to illuminated manuscripts, to printed books, to digital files. Think about how each generation stands on the shoulders of the previous ones, building higher, seeing farther, understanding more. But also think about how some things remain constant. The curiosity that drove a Babylonian scribe to explore number patterns is the same curiosity that drives a modern mathematician. The satisfaction of solving a difficult problem is the same across millennia. The beauty of an elegant proof or a perfect calculation transcends culture and time. Mathematics, in this sense, is one of the most universal human languages. It works the same way regardless of who's doing it, when they're doing it, or what language they speak. A quadratic equation solved in ancient Babylon gives the same answer as one solved in modern Tokyo or New York or Cairo. That universality is profound. It suggests that when we do mathematics, we're tapping into something fundamental about reality, about the structure of the universe itself. The patterns we discover aren't arbitrary or cultural, they're real, they're true, they're consistent. The Babylonians found some of these patterns 4,000 years ago, and they're still true today, and they'll still be true 4,000 years from now. If humans still exist, then if we manage not to destroy ourselves or our civilization, future people will still be using algebraic methods that can be traced back, through many intermediaries, to clay tablets pressed by Babylonian scribes. That's a connection across time that's almost spiritual in its significance. So the next time you solve an equation, or calculate an area, or check the time, spare a thought for the ancient Babylonians who made it possible. They couldn't have imagined you, sitting here in the future, learning about their achievements through a glowing screen that transmits information at the speed of light. But you know about them. You're thinking about them. You're appreciating their genius. And in that moment of recognition, the gap of 4,000 years collapses. You're connected to them, human mind to human mind, across the vast expanse of history. Thank you for joining me on this journey through Babylonian mathematics. Thank you for caring about the history of human knowledge. Thank you for being curious enough to watch a video about ancient clay tablets and sexagesimal number systems. The world needs more people who care about where our knowledge comes from, who appreciate the long struggle of human beings to understand the universe and our place in it. If you enjoyed this, please like, subscribe, and share it with someone who might find it interesting. Check out my other videos on the history of mathematics, computer science, and technology. And let me know in the comments what you'd like to learn about next. Sweet dreams, and may your own mathematical endeavors be as successful as those of the ancient Babylonians. Remember, you're capable of more than you think. If people 4,000 years ago could invent algebra using nothing but clay and reeds, imagine what you can do with all the tools and knowledge available to you today. Now go forth and calculate something. The Babylonians would be proud.